Morning.
Yes, how are you?
Yeah, fine.
Rabera, how are you?
Good morning.
Yeah, so I'm assuming this is FEE 102, Physics B or Physics 1B, whichever you may refer to it. And I'm told your semester began last week. Is that right?
Yes.
And you've already started the labs?
Not yet. I think this Friday.
Okay. So sorry for last week. I didn't have the timetable, so I didn't know that we were supposed to meet on Thursday. But thanks to your class rep, we got in touch and we agreed that we have to begin this lecture today. So my name is Mr. Konda Justice, and I'm the one in charge of this unit. So the fact that this unit is linked to the lab, I think we'll also be addressing issues to do with labs. So if you have an issue with the lab where you don't know what to do, maybe we'll get time and shed light on your lab aspect if need be. But I'm assuming all of you are fine, and we are set to go. So the class representatives will still remain the same. Are there changes for this unit? Yes. Do we still maintain the class reps?
Yes.
Are they both here?
I mean,
Are they with us here?
yeah.
Good. So there is Muita and the other one is Abdi.
Yes, Abdi.
Abdi, good. So we hope to have an interactive session. If there is a concept you don't understand, please do ask. And then we can be able to help one another, because I'm assuming that you did well in Physics 1B, 1A, which was taught by my colleague. And there are no complexities in this unit. Of course, I'm going to use a few concepts from the Physics 1A or Physics A for that case. All right? Are we okay?
Yes.
Yes, we are.
Good. So without wasting much time, I think we can move to, I need to record this. So as I said that, just a minute, please. It is not our first time to have lectures online. So I believe we understand the challenges that are there. But then the fact that the lectures are being recorded, that does not mean that you absent yourself from attending this lecture. Because at times, in fact, I needed to put on the attendance so that I also get your attendance as well, right? So, of course, those will not attend 2/3 of the class, you'll be exempted from the examination. And for engineering, your exams are physical, right?
Yes.
Your exams are physical, good. So, and you know, you can't compare physical exams and online exams. Physical, online, of course, it's more of open book, but we are going to mix both the two in terms of the assignments. All the assignments will be done on SOMAS, all right? So, are you able to see my screen? Hello?
Yes.
Just a minute. We'll go straight to the course outline. We are all able to see my screen? Hello?
Yes, but not very clear.
Yes.
You can see the course outline?
Yes.
Is it visible from your side? Yes or no?
Yes.
Good. So this is Physics 1B or Physics B, and it's being done by several groups. We have civil, we have mechanical, geospatial, environmental, and biosystems groups. So in this case now, what happens is that as you did your Physics 1A, the exams, we normally meet as a team, then we set your exams. So maybe I give one question, the other colleagues, each one of them gives a question. Then at the end of the day, we have an exam. So that actually signals the difficulty level, right? That means that it is not kind of an easy exam. So you have to up your game, ensure that you understand the concepts right. Yeah. And from experience, this most students never perform well in this unit. I don't know why. I don't know whether it's because of the electric and the magnetic aspect, but being electrical students, I think the performance for over years has been higher compared to other groups, right? Now that does not mean that you keep off. That does not mean that you know everything, because the presentation and the methodology of delivery of this content at times will differ. Whatever I taught last year may not be the same thing I'm teaching this year, because I have to make some few changes here and there. All right. So the course outline is in three categories. The first category is electricity and electrons. And in this case, we try to understand what is electricity all about, being electrical engineering. I think this one we can say that you go read for yourself, is it? Or the electricity aspect is embedded in you. Electrical engineering. Am I right? Hello?
No.
No. I mean, come on, we are electrical engineering students. So issues to do electricity, I mean, we are okay, right? So we just say, I mean, that one is covered completely. Marigu, is that okay with you?
I think.
These are, come on, these are electrical engineering students. And when you're talking of, you want to teach them electricity. I mean, are you sincere? So that one I'll go through very fast, all right?
But the name.
It is?
That is in the name.
Is only the name. All right. So under this, we focus more on electrostatics. That is the charges that are at rest. Then we look at the moving charge, look at the application of the moving charge in terms of the cathode ray oscilloscope. We've been able to use this in the lab. And then we look at the conductors, insulators, and semiconductors. Under semiconductors, we'll be looking at the diodes. And I know you've been able to use this in your daily undertakings in terms of the labs and maybe your practice outside there, I don't know. Then we look at rectification. This is high school, actually. Full wave and half wave rectification, AC current, inductors, right? And then we look at the transistors and their connections. So that will cover electricity and electrons, which is the first category of our course outline. Then the second aspect will be looking at magnetism and electromagnetic waves. where we look at both the magnetic and magnetic fields, the type of magnetic materials, electromagnetic induction, then force on a conductor, Lenz's law, then finally we look at electromagnetic waves. All right? Then the last aspect will be on radioactivity and light. So we look at the theory of radioactivity, types of radiations, isotopes, X-rays, then photoelectric effect, then finally we look at the polarization. Reference books, some of these books you can get them online. Some of them you can go to the main library at main campus there. Those are your neighbors. You can walk in and get any of these books for your reference, all right? But some you can get them online. Are we okay with the course outline? Is there something you want me to delete from the course outline? Assuming that you know you're okay with that. Abdi? Are we okay with the course outline?
Yes, we're okay with the course outline.
Yeah. Is there anything we should delete that you feel members know? Abdi?
No, I think it's okay. I think the course line is okay.
Course outline is okay. So before we move to our lecture, our first lecture today, now the rules of the game is that for me, I normally give 2 cuts. There is cut 1 and cut 2. Then there is assignment 1 and 2. Now, the 2 cuts will be done online. The 2 assignments will be done online. We are all aware of the online platforms that we have. And basically, I normally go for SOMAS. I hope we are all conversant with that. Are we okay with SOMAS?
Yes.
Yes.
We okay with SOMAS?
Yeah.
So, and apart from the 2 assignments and the 2 cuts, depending on the content that we'll be working on, you can have an assignment. Now, the assignments and the cuts cannot be done during lecture hours. We only have 2 hours per week, so we have to make maximum use of those 2 hours. So the assignments will always be done over the weekend, right? Are we okay?
Yes.
I'm in class, I will call it. So over the weekend, either on Saturday or Sunday, that is when we'll be having our cards, our assignments, and maybe some few questions over the week to discuss. All right? So ensure that you know how to log in and you know how to make your submission. So that will be effective, I think, next week. So I think we are okay with that. Any question before we start? Any concern? Hello? So I'll assume there is no problem. We can proceed on with our first lecture. And from the course outline, we are supposed to be looking at electrostatics and Coulomb's law. And then we move to capacitors. Then we see whether we can tackle something on current electricity, right? So are you able to see my screen? Hello?
Yes.
Yes, yes.
Hello?
Yes, we can.
Yes, we can.
Yes.
So, as I said earlier on, that we have 2 types of charges. I mean, you can have a charge at rest, and then you can have a charge that is in motion. That's why we are talking of electrostatics and electricity. So electrostatics is basically the study of a charge that is at rest, right? And we are saying that the charge can either be positive or negative. Now, what defines a positive charge? What defines a positive charge? When do you say that this object has a positive charge? We all know from your chemistry in high school that an atom consists of the protons, the neutrons, and the electrons. Now, the protons are positively charged, electrons are negatively charged, but neutrons have got no charge. So if you have an object with more positive charge, more protons than electrons, then that object will be positively charged. Now, another object that is negatively charged, that means we'll have more electrons than the protons. Is that okay? Hello?
Yes, sir.
Yeah. So basic knowledge, like charges repel and like charges attract. I think we're okay with that. So therefore, by electrostatic, we mean that the charge that is not moving at all, the charge that is stationary. So if you have, let's say, two charges that are stationary, maybe I can create some. Just a minute. So I'm assuming you still can be able to see my screen? Yeah.
Yes, we can.
Yes, we can. I just want to demonstrate something here. Let's be patient, it's a bit slow. So if you have two charges, charge A and charge B, then of course, if they are of the same charge, there will be a force of repulsion that will be created. Why it's not coming in? But if you have a positive and a negative charge separated at a distance d, then a force of attraction is bound to be experienced. We proceed on. Once it's on, I can demonstrate that. So of course, units of for electric charge, we know that we have the SI units of measurements, right? So when you're talking of charge, charge is measured in coulombs, right? And the symbol is C. But electric current is given as charge, the rate of flow of charge, that is charge per unit time. So therefore, charge is actually electric current times time. But we know electric current is measured in amps. So therefore, 1 coulomb can be said to be 1 ampere second. Is that okay?
Yes.
I don't know why my canvas is not coming. Just be patient, please. I wanted to demonstrate this so that you're able to see. So therefore, if you are given 1 coulomb, then that is the same as 1 ampere second, right? Please be patient a bit. I don't know why it's not coming. It is here. So, so therefore, we are saying that 1 coulomb is 1 ampere second, and we all know that an electron has 1.6 times 10 raised power negative 19 coulombs, right? So if you're talking of 2 electrons, then you take 2 times 1.6 times 10 raised power negative 19 coulombs, right? Now, similarly, you may have an object that has got more positive charge than the negative charge. That means it's positively charged. So if it is positively charged, then of course it will be deficient of electrons. And in this case, if an electron has a charge of negative 1.6 times 10 raised power negative 19 coulombs, then the proton will have positive 1.6 times 10 raised power negative 19 coulombs. Are we okay with that? Let me use just a minute. Let me see whether I can use this, because it will sound abstract if we don't demonstrate this. Just a minute, please. Minute. Let me see comments. This is going to work so that we demonstrate. All right, let's give it time. It is okay. So quantization of charge, we are saying that charge is quantized. Any given charge is an integral multiple of the elementary charge. Now, the elementary charge is normally given as the smallest amount of charge, which is the charge of an electron, and it's actually 1.6 times 10 raised power 19 coulombs. So any charge should be an integral multiple of this. Any charge should be an integral multiple of that. That means you can have an E, a charge of E, a charge of 2E, because E is actually our elementary amount of charge, which is an elementary particle. Then we can talk of 3E, we can talk of -2, -E, -2E, -3E. Because we know integers, we are talking of 1, -1, 2, -2, like that. So charge is always an integral multiple of an elementary charge. So that means you cannot have 0.7E, you cannot have 2.5E. But you can have 3E, you can have 4E, you can have -2E and negative. Now, the reason why it's negative or positive is because we say that if a body is positively charged, then it has more protons than electrons. So it will have positive E. But when it is negatively charged, then it will have more electrons than the protons. So therefore, it will be negatively charged. All right? Hello? Are we together?
Yes.
Oh, no. Don't know how we are going to survive because the canvas is not working. Why? So charge is quantized, very important, quantization of charge, that you cannot have a fractional kind of charge. a charge must be an integral multiple of a charge of an electron. Right, I think now it's fine. So basically, what you're saying is, I'm assuming you can still see my screen? Hello?
Yes.
Yes.
So what you're saying is that from electrostatics, you can have a charge Q here, this is Q1, and another charge Q2, right? Now this Q2 is at a distance d from Q1. Therefore, if we know the quantity of this charge Q1 and Q2, let's say this is positive charge, and then this is also positive charge. So that means that there will be a force of repulsion between the two charges, all right? Because we actually say that like charges repel and unlike charges attract. So this F will be in that direction, and then this F will be in the opposite direction. But if this is our negative, you have Q1, which is negative, and then our Q2 is positive. Then we are saying that there will be a force of attraction between the two charges. Remember, they are still at a distance d. So what you're trying to do under electrostatics is determine the quantity of this force that comes into play when the two charges are adjacent to each other, right? Now, therefore, if I move Q2 towards Q1, I'll do some work. So therefore, again, the work done, the aspect of work done, which comes from your physics A, we'll see how to calculate the work done in moving a charge Q2 towards Q1 or Q1 towards Q2. Now, that amount of work done, we can also look at it in terms of, for Q1, we can look at what is the influence within which, the region within which this Q2 feels a force due to Q1. In other words, the Q1 defines a certain field around itself so that any visitor that comes close to this Q1 will experience a force. Now, this region created by Q1 within which an object experiences a force due to Q1 is what we are referring to as the electric field, E. All right? So we are talking of, we have an electric field, E. We are talking of the work done. We should be able to compute the work done. And then the electric potential, B, for such kind of stationary charge. Now, with this, therefore, we needed to determine the force F, the electric field strength E. This is just like the gravitational field strength, the gravitational field strength G. So instead of G, we are looking at E, electric field strength. Then we look at the work done, because this is charged. You know, you've been looking at masses, an object of mass M1 and M2. But now we are talking of an object of charge Q1 and charge Q2. Now Q1 and Q2 is in terms of coulombs. The masses under physics A was in kilograms, right? So please understand the transition. We are not talking of something that is absolutely new, but we are just building from the mass in kilograms to a charge in coulombs, all right? Are we okay with that? Hello? Class, are we okay?
Yes.
Any questions so far on this?
Yes.
We okay, good. So back to my notes. Charge is quantized. Again, we are saying that you cannot have 2.5 or 0.7 E. Conservation of charge, we know that the number of charges in an isolated system. Now, what is an isolated system from your physics 1A? What is an isolated system? Hey. What is an isolated system? Mutuku, what is an isolated system? Anybody? Sherry, what is an isolated system from your physics 1A? All right, so I think I'll bring that into your assignment so that I see whether you're getting this. Now, whenever we say a system is isolated, that means that there is no external force that is acting on that system. All right? So if there is no external force acting on the system, then the laws of conservation will come into play. Did you learn something about that? Or that is a new concept? Because now, if you don't know what an isolated mass is under the mechanics, then now when we transform to electricity and electrostatics, it's going to be messy. Yet, I was very happy when I was given electrical engineering. I knew these guys are very sharp. That was my assumption.
Don't mind, don't mind.
Huh? We okay, yeah? Marigu?
We are very okay.
Even if things seem tougher, you toughen yourself, is it?
Exactly.
Yeah, so go read about an isolated system. So we are saying that there's no external force that is acting on the system, right? Now, under such case, we are saying that you can not create nor destroy charge, but you can only transfer charge from one system to another. So long as you're within that isolated system kind of, right, context. So therefore, the net charge will always remain a constant. We are saying that you can neither create nor destroy charge, but you can only transfer charge from one point to another of the system, right? So charge can neither be created nor destroyed, but it can only be transformed from one form to another. Maybe you have some static charge, you transform it to electric charge, because we are actually electrical engineering students. We like moving charges and not stationary charges. But you cannot understand a moving charge unless you know the physics of the stationary charge. Is that okay? Hello?
Yes.
Yes, it is.
Yes, it is. Good.
Yes.
So, sorry, that should not scare you. I'll see how to delete that from. Now, there is the Coulomb's law. Under Coulomb's law, if I give you two charge Q1 and Q2, and these two charges are actually at a distance d from each other, then the Coulombic force F should actually be directly proportional to the product of the two charges, because under mechanics you had F is equals to mechanics. Gravitational force is given by G, and somebody remind me, G what?
M1, M2 over.
G M1, M2 over R squared. You remember this? Hello?
Yes, we do.
So the gravitational force was actually directly proportional to the product of the masses M1 and M2, but inversely proportional to the square of the distance between the two charges. This is the gravitational constant, the universal constant, all right? Then the same concept here, we are saying that if you have two charges, now what we need to know is the medium within this, which separates these two charges, Q1 and Q2. So if this is within air, then we'll see how to compute our G in terms of the Coulombic force. So therefore, Those who are coming late, please. So we are talking of this F should actually be directly proportional to the product of the charges Q1 and Q2. But again, the same force should be inversely proportional to the square of the distance. So maybe we can call this R so that it makes sense. We are not deviating from your mechanics. All right? Now, the moment you remove this proportionality sign, you bring in a constant K. So K, Q1, Q2 over R squared, right? Now, where K represents the medium within which these two charges are placed. So that is 1 over 4 pi epsilon naught, sorry, this is pi, 1 over 4 pi epsilon naught. So you can talk of where epsilon naught is the permittivity of free space. Assuming this is in free space, then this is E naught, epsilon naught, which is given as 8.85 times 10 raised power negative 12. Some books, power 9, sorry. Some books will give you 9, some books will give you 8.85, right? So we are saying that our F is directly proportional to the product of the two charges, Q1 and Q2, but inversely proportional to the square of the distance between the two charges, right? Where K is 1 over 4 pi epsilon naught, which is a dimensional quantity. And our K is 1 over 4 pi epsilon naught, which when you substitute pi and epsilon naught should be 8.85 times 10 raised power negative 12, sorry. Yeah. So substitute this epsilon naught and pi as 22 over 7, then you'll end up with this as K. So if you're given a question, then it will come in the form of you're given the value of K, you're given Q1 and Q2, and you're given R, then compute the force. Now this force, you'll either state that it is attractive or repulsive depending on the nature of the charges. If they are like charges, then we say that that will be a repulsive. But if they are opposite charges, then this will be a force of attraction, right? Just like you have a mass M1 and M2, then you are trying to look at if this is within a gravitational field of gravitational field strength G, then how do you compute the gravitational force F? So we've not changed anything from mechanics, right? Is that okay? Hey, class. I think we need to pause. We need to
It's okay.
Martin Wawira, are we okay?
Yes, we are.
Good. So we proceed on. We proceed on.
It's okay.
It's okay. So therefore, when you talk of 1 microcoulombs, then that is 10 raised power negative 6 coulombs. We all know that. You can have microcoulombs. You can have picocoulombs. You know those prefixes. So therefore, F is equals to 1 over 4 pi epsilon naught Q1 Q2 over R squared. Now, for air, where we are saying epsilon should actually be absolute permittivity of the material in terms of you can have a vacuum. These two charges can be within a vacuum system, or they can be within some dielectric medium. So maybe with they have some kind of insulations. You need to compute the permittivity of the material, right? So therefore, we are saying that epsilon should actually be K epsilon naught. In other words, K will actually be epsilon over epsilon naught. So for air, K is 1. The value of K is 1. So that's why we are saying that epsilon, the permittivity, should actually be equivalent to the epsilon naught, which is the absolute permittivity. Are we okay? Now this K is actually the dielectric constant. Now when we're looking at the capacitors, I think we'll be able to discuss the dielectric material and see how to compute this value of K. So we are saying that K should be equals to epsilon which is the permittivity of the material over the divided by the absolute permittivity epsilon naught for free space, right? So that will give you the K value. So we'll still go deeper into this, or relative permittivity maybe, because you are trying to divide the two. Now I say that whenever a charge creates a force field within itself, if you bring another charge, it's just like at night, the universe defines a force field by its darkness. Maybe let me say the earth. So if you have a torch can be able to see through the darkness. So therefore, that kind of darkness is what we are referring as the force field, which actually gives you the region within which the charge experiences an electric force. All right? Yeah. So consider, back to my canvas. I think I had explained this earlier on, that if we have a charge Q, let's say this is Q1, there is another charge Q0. Now this Q1, maybe it's positive, it defines a region within which, let's say Q0 is at infinity. Now bring Q0 towards Q1. So therefore, within this region, Q0 will experience the force due to Q1. Are we together then? Are we together?
Yes.
Hello?
Yes.
So we are saying Q0 will experience a force due to Q1 when it moves within this region. So therefore, this region can be defined as an electric field E within which Q0 will experience a force due to Q1. Right? And we are saying that E is actually the electric field strength. E is force per unit test charge Q0. Now, we are talking about test charge because of its negligible mass. The mass is so small that it cannot change the field due to Q1. If your Q0 is a mass, not the mass, sorry, the charge is too small that it cannot change the field due to Q1. But if this Q0 was of a higher charge, then as you bring it close, it will be able to interfere with the magnitude of the electric field strength E due to Q1. Are we together? Hello?
Yes.
Yeah, so this has got a very small quantity of charge so that it doesn't change the field. Otherwise, you make it with a greater amount of charge, it will change this field E, all right? But we say that F is what? F is K, where K is 1/4 pi epsilon naught, Q1, Q2, right, over R squared. Maybe the distance between this Q and, so this, in this case now, this Q2 should be actually Q0. Because this distance between Q0 and Q1 this is R. This distance is R. All right? So over R squared. So therefore, if we want to find the electric field strength E, or G, if it is under physics 1A, we are talking of G. So in physics 1B, we are talking of E. So I'm just replacing G with the E. All right? Because we know G from your mechanics, G is what? G is given by force per unit mass, right? F over M. So here we are saying that this is F over Q0. And Q0 is our test charge. So therefore, if you substitute F here, you'll end up with E should be equals to K, Q0 cancels out. So you'll have KQ over R squared. Is that okay? Hello? Are we okay with that? Without your response, I can't move on.
Could you kindly repeat?
Okay, I'll repeat. From your mechanics, you know that the gravitational field strength, the G, is given by force per unit mass. Now, in electrostatics, we are saying that the gravitational field E, the electric field strength E is given by force per unit test charge. And we are saying that this test charge is like a torch. A torch cannot change the magnitude of the darkness, right? It is dark at night, is dark. So the only thing is that it can only probe that darkness, all right? So a torch, look at the torch with a small quantity of charge that cannot change the magnitude of the darkness at night. That is what we are referring to as the test charge. And we are saying that if that test charge is at a distance r from Q1, therefore the force, the Coulombic force F, should be given by K Q1 Q0 over R squared. But since E is actually F, the force per unit test charge Q0, therefore, if you substitute F, you'll end up with KQ, this should be KQ1 over R squared. Is that okay? Hello?
Yes, yes.
Now, the Q0 is a positive charge. Is a positive charge, which has got a very small amount of quantity charge that cannot be able to change the magnitude of the electric field strength, E, G2, Q1. Hello? Marigo, hey, I need to hear your voice. Moses, is everything okay? Moses, unashikanisha kweli?
Yes, sir.
Tuku Josephat,
Kidogo.
I can see you.
I'm also understanding.
Oh, you are also understanding. Let me see these other
Yes.
guys who are hiding down there. Daudi Abdirabi. Hey, this is a Kenyan. Daud. Hey,
Yes, sir, yes.
are you okay?
I'm not like,
Are you a Kenyan?
no.
No. All right.
Are you Ethiopian?
Oh, that is an Ethiopian, maybe. Kamau Brian, hey, say something. Are we okay?
Yes.
Good. Oliver Oyeke, because I know some people, they log in, then they disappear. You think they are here when they are not here. Oliver,
Yes.
are you with us?
Yes.
Good. Safari, Alex.
We are together.
We are together. Good. Stella Njambi. Hello. Hey, Stella. This one switched on, then she disappeared. Okay. So Stella, I will take note. Stella is not around. If you're around, please raise your voice so that we can hear you. Then again, I think I will demand that. Oh, you are here. Good. Stella Njambi is here.
Yeah.
Washika Miracle. Hey, this Miracle guy. Where are you?
Yes, I'm around.
You're around. Good.
Yeah.
So now, why are those cameras off? Being the first lecture, I think they are supposed to be on. Then, yeah. Class rep, they should be on, right? Good. So we can proceed on. So electric field strength, I think we've discussed this. We'll go through the notes. E should be equals to F over Q naught, where Q naught is our test charge. It's so small that it cannot change the magnitude of the field E. All right? So we are saying F is equals to 1 over 4 pi epsilon naught R squared Q naught Q1 or Q. Then E is F over Q naught, where E should be actually 1 over 4 pi epsilon naught R squared multiplied by Q. Yeah. Then the unit for E. So force, the electric field strength E is force per unit test charge Q naught. So therefore, force is in newtons from your mechanics, and then Q naught is in terms of coulombs. We say charge, the SI unit for charge is the coulomb. So therefore, the electric field strength E is defined in terms of newtons per coulomb, right? Hey, are we together?
Yes.
Good.
Yes.
Example, can somebody read, please? Who should read? I think I should choose who to read. Maybe. Hey, Musa Osman, can you read? Musa Osman. Read. We are time back. Musa Osman?
So I can't see properly.
Are you blind or what?
I can't see the screen properly.
You're using your phone?
Yeah.
I think I thought we all came with laptops to the university. You don't have laptops, all of you? Hello? Who is attending this using a laptop? You can read. Engineering students. These engineering students, they don't have laptops. You know who an engineer is, I mean. Or you are just doing the course for the sake of it. Do you know who an engineer is? Huh? Emmanuel Otieno, who is an engineer? Emmanuel Otieno?
An electrical engineer, which engineer?
Hello, sorry for that interruption. Emmanuel Otieno, can you read the question, or whoever is ready can read? Hello? The class rep,
Consider point charge Q1.
Can you read loudly, please?
Consider point charges Q1 negative plus 2
microcoulombs.
Coulomb, microcoulomb, or what? Q2 negative plus 4 Q3
microcoulombs
6 Coulomb, and Q4 negative 6. Placed at 4 corners of squares as shown in the figure. Each diagonal is of length 2 meters.
So calculate
Calculate
the electric field strength at the center of the
intensity
square,
at the center of the square.
and then determine the
What will
force.
be the force on the charge of?
Okay. So now, this is our question, but we have 4 charges, Q1, Q2 up to Q4, and they form a square. They form a square of length 2 centimeters. So this is 2 centimeters each. Now we are supposed to compute the electric field strength at the center of the square. For a square, this angle should be what? 90 degrees? Hello? Given a square, the angle between the diagonals is 90,
Yes.
right?
Yes.
Yeah. So if that is 90, then if we take this to be our x-axis, this diagonal to be our x-axis, then this diagonal will be our y-axis. I think I need to demonstrate this. Some members will not see this. But is it a must you see everything? Being an engineering student, is it a must you see everything?
Yeah.
Who said so?
Observation is key.
So, what you're saying is that this is our square. There is a charge here, Q. There's another charge here, Q. Q, I don't know which is which. This is Q1, maybe Q2, Q3, and Q4. Now, we'll treat this diagonal to be like our X. This is X. And this diagonal to be like our Y. So this is Y. This is Y. So therefore, for us to get the resultant electric field, this angle is 90 degrees, then it will be, it's like we are computing the diagonal, right? The hypotenuse here. Because now when you resolve, you end up with something like that, right? But this angle is 90 degrees. So if this is the base, this is the height, therefore we can compute this diagonal here. So back to our question, this is what we need to do, right? Now, E1, so this will have E1, E2, E3, up to E4, the electric field strength. And E1, we said it is 1 over, that will be 1 over 4 pi epsilon naught r squared times Q1. You remember we said E is equals to F over Q naught. You remember that? Hello? Hello?
Yes.
Yes, yes.
Yeah. And what is the distance from the center? Oh, we are told each diagonal is 2 meters long. So therefore, from this charge to the center, it will be 1 meter. This charge to the center is 1 meter. So therefore, our distance R for each of them is 1 meter, right? So when you substitute, your K is 9 times 10 raised power 9 Newton meter squared over Coulomb squared. Then you'd end up with 18 times 10 raised power 3 Newton coulombs. All right. Now, I should have begun by asking you to compute the force maybe between Q1 and Q3. So the force between Q1 and Q3, you see this is positive, this is also positive. So that will be a force of repulsion. All right. So maybe that will be given by negative. Now in this case, we'll have 1 over 4 pi epsilon naught, which is the value of K, 9 times 10 raised power 9. Then multiply by this Q1, 2 microcoulombs. Micro means what? Times 10 raised power negative 6. Then multiply by 6 times 10 raised power negative 6 coulombs. Then divided by the distance of separation of the two is what? 2 meters. So 2 meters squared, which is 4. So this is 1 meter squared. which is just 1. So you compute E2, compute E3, and compute E4. All right? Now we say that if this is your X, then this will be your Y. So therefore, E3 and E1 constitutes the electric field strength along the X, then E4 and E2 constitutes the electric field strength along the Y. Now, this will be repulsion. They repel each other, so that's why they're acting in the opposite direction. And then E4 and E2, they are of opposite charge. There is Q3, sorry, there is -6 microcoulombs and +4 microcoulombs. The two will act in the same direction because they are of this of opposite charge. They tend to attract. So attraction means that the electric field strength will be enhanced along the Y, but along the X it will be weakened. Simple. All right. So once you've been able to compute all this, along the X we said it is E3 and E1. And since it's the field is being weakened, you subtract, you end up with that. Along the Y, they are of opposite charge. The field is actually being enhanced. We add that. Then you'll end up with that. And we want to compute the hypotenuse because we needed the resultant electric field strength, which is actually given by the hypotenuse. So you embrace the Pythagoras theorem from nursery. I think that's okay. So you end up with that. Now, electric field strength is a vector quantity. A vector quantity is defined by magnitude and direction. So therefore, how do we define the direction? Direction is defined by the angle. So we need to compute this angle. For us to get this angle, we embrace the tan theta should be equals to, if this is theta, then tan should be opposite, which is E of Y, over the adjacent, which is E of X. So you'll end up with 2.5 degrees. I mean, this is in radians, I think. Converting to degrees, you end up with 68. So therefore, our resultant electric field is 9.7 times 10 raised power 4 Newton per Coulomb, which is acting at an angle of 68.2 degrees with respect to the x-axis. The force, the second part of the question, you are supposed to compute the force on a charge of 5 microcoulombs placed at the center of the square. So if you have a charge of 5 microcoulombs here, what will be the force it is going to experience because of the electric field strength E that we've obtained here? Now we know that E is actually given by F over Q. So therefore F should be Q naught E, and our Q naught is 5 times. This is a test charge because we don't want it to influence the electric field strength E. So therefore that will be 5 times 10 raised power -6 multiplied by the resultant E that we've obtained, then we get that. All right? Question? Or if you've not understood, hey, are we here? I may be talking to myself here. Are we okay? Jerry? Chuleva? Are you here with us?
Hi, yes, I am. I just, okay, I feel like you're going a little too fast.
But these are electrical engineering students.
Okay. But please just slow down a bit.
Okay.
Thank you.
Yeah. Gacheru, Ian. Gacheru, where are you?
Yes.
sir.
Are we together?
Yes.
This stuff is okay, right? Mm-hmm. Yeah, Mwita. Are these guys getting it, Mwita?
Yes, sir, we are getting you.
Sylvia? Giworit. Hey, is it Giworit or Worit? Worit, Sylvia?
Yes.
Is everything okay?
Yes.
Good. Kamau, Brian. Kamau,
Yeah.
can you respond? Yeah.
Yes. Yes.
You okay?
Yes.
Good. Kiprono Festus?
Yes, we're okay.
Okay. Kome? What have you understood, Kome? Armstrong? Kome Armstrong, absent? Kome, where are you? I think if you're absent, if you don't confirm that you're present, we remove you from the meeting, right? Kome, are you with us? Oh, this one should be removed. He's not here. Kome, are you with us? Oh, this one should be removed. Let him go. All right, so let's proceed on. I'll slow down. What we've done is we've computed the electric field strength in all the directions.
But
Then we say
about
this is
the attraction between the particles. I think it's okay.
Yeah,
Yeah,
you're saying?
it's okay.
It's okay.
Yeah, present. It's okay.
So E1 and E3, they are same charge. They should repel. They should actually repel.
It's okay.
So when they repel, what happens? They weaken the field. This one, they will strengthen the field. That's why this you add and this you subtract, correct? Simple. I think I'm teaching in a layman language so that you can. Yeah. Oh, that's Armstrong.
Yes.
Oh, I know I was just about to remove you from the meeting because I said if I call your name and you don't respond, I throw you out. Yeah, an engineer should always be present, even when things are not adding up, right? Even if the city is burning, just present yourself there. Name electric field lines. Now, an electric field is defined by electric field lines. The more closer the electric field lines are, the more strong the field is. Simple. The electric field lines will always move from positive to negative. So that's why you can see for positive they're leaving, for negative they're coming in. Is that okay? So if you have positive, negative, of course you'll have electric field lines leaving the positive charge towards the negative charge. Then if you have both of them positive, of course they will create a neutral point X. This is high school, right? Hello? Hello?
Hello.
This is high school. This is high school concept, right?
Yes.
Now, what if you have two plates? One is negative, the other one is positive. Positive plate, negative plate. Like we are talking about a capacitor, which has actually two plates. One is positive, the other one is negative. The electric field lines will emanate from the positive towards the negative. Now, when they are evenly spaced, this distance, if this distance is common for all of them, then this is a uniform field. Otherwise, if, let's say, I think I should go to the canvas Chrome. So what you're saying is that if this is the positive plate and this is the negative plate, then the distance between the electric field lines should be equal. So this will give you a uniform electric field, right? But now, at some point, you realize that you have such like electric field lines. Now you can see this distance is not more or less the same as the rest. So here you expect a non-uniform field This is also non-uniform field here, but at the center, this is a uniform field. Now, when the field lines are so close to each other, let's say you have such a scenario here, then this is a strong field. But if they are far away from each other, then this is a weak field. So this is weak and this is a strong field, right? This is weak, this is weak field, this is a strong field. So note that the electric field lines emanate from positive to negative, and that the uniformity of the electric field lines defines a uniform field. The closer the electric field lines, the stronger the electric field. And remember, please don't forget that E is equals to F over Q naught. Now this is for point charge. Now what if you have a plate? A plate, let's say this distance from positive to negative is D. Now, since you are talking of positive and negative, there comes electric potential V, all right? So the electric potential, the potential between the positive and the negative, this is negative plate, is what? V. The distance of separation of the two plates is D. Therefore, your E, you cannot talk of F over Q naught. There's nothing like that here. E should be equals to V over D. Hey, are we together? Are we together? I think I've slowed down. I've slowed down. Are we together? Hello?
Hello.
Are we together?
Yeah.
Good. Let's move on. So that's where we are. Properties, I think you can go through this. These are self-explanatory. I don't need to read them for you. Then electric potential energy. So this is actually the work done to bring two charges from infinity to each other to form a system, all right? So if the two are at infinity, bring them together, then you'll be doing some work. That work is actually electric potential energy, right? And we know that work is actually given by force times the distance. Now we know force is, for this case, it will be, if you're bringing Q2 close to Q1, then the force will be K Q2 Q1 or Q1 Q2 over R squared, all right? Then multiply this by the distance R. Of course, that will give you Q1 Q2 K Q1 Q2 over R. So, which is more or less the same as this here, the work done. So you can approach this from the fact that we know that the work done is force times distance, you still get this. Or some books will tell you that the work done is actually, or maybe you get this from V, the potential difference, the electric potential is actually the work done per unit charge, which is W over Q naught over Q2. So when you want to get W, multiply both sides by Q2, you end up with the work done is actually Q2 multiplied by the potential within which that charge is supposed to move. So if you know V, therefore the work done, we can also get it by taking Q2 times V, which gives you 1 over 4 pi epsilon naught Q1 Q2 over R. Is that okay? Class, is that okay?
In the previous slide.
Yeah. Oh, previous slide. Question there? No. Are we okay with how to compute? I think you move slowly. I've been warned that I'm very fast, despite the fact that these are engineers. I think I should slow down. We are saying that the work done is force times distance. Hello, you are saying? K Q1 Q2 over R squared multiplied by R. So 1R goes, you'll have K, Q1, Q2 over R. Now we are saying that V, the electric potential, is given by the work done to move a unit charge, in this case is Q2, from infinity to the point of interest within the field. So therefore, from this, we are saying that the work done is actually Q2 multiplied by the electric potential V. So if you know V multiplied by this, you still get the same thing. Is that okay? Hello? Class, are we together?
Yes.
Good. So therefore, we can get electric potential energy. The work done is more or less the same as the electric potential energy because we know that the unit of measurement is the joule. So therefore, this work done becomes your electric potential energy. And again, if you have three charges, Q1, Q2, and Q3, where Q1 is positive, Q3 is positive, and Q2 is negative, then the electric potential energy of this system will be given by Q1, Q2. Of course, we factor out K. And then between Q1 and Q2, you can see that Q2 is negative. That's why these are negative. Q3 and Q2, Q2 is negative. This will give you a negative. But then this is positive, so that will give you a positive. Is that okay? Hello? Hello, class?
Please repeat that step.
Okay. What you're saying is you have Q1, Q2, and Q3. Now, Q1 is positive, Q3 is positive, and Q2 is negative. We know that the electric potential energy is given by 1 over 4 pi epsilon naught Q1, Q2 over R, right? So what we need to know is the distance of separation. And the distance of separation of the charges is R13, R23, and R12. So between Q1 and Q2, what is the work done? Sorry, what is the work done? So the work done is given by K, Q1, Q2 over R. But R is R12. But this is negative, so that's why we have a negative. Then this and this, these are negative, that's why we have this negative. K is factored out, that's why you have 1 over 4 pi epsilon outside the curly bracket. And then these two are positive, so that's why. Is that okay? Hello?
Yes.
Are we in agreement with that? Class, are we together?
Yes, sir.
Yes. Now,
Yes.
I need to shed light on the fact that you can have quite a number of charges, Q1, Q2, Q3, and maybe Q4. So you have the whole of this distance, and then you have this inter distances, all right? You can have this and that. This can also interact with that. Or you can put them in form of a triangle. Then we are saying that F could actually be the resultant force F due to all these charges should be given by K, Q1, Q2 over maybe this distance is R1 over R1 squared, then plus all these other interactions. You can have K, so plus K, Q1, maybe Q1 is interacting with Q3, all right? And this distance is R maybe 3 squared. Let's say this is R3. Then maybe plus, maybe Q1 is also interacting with Q4. Now, again, Q3 will interact with Q4. Q2 will interact with Q4. So you'll add all this. So at the end of the day, you'll end up with your resultant force F. So F should actually be the summation of, so you can have K, the summation of from the first charge to the nth charge.
Excuse me.
Of course, the first charge is Qi or Q1. Maybe I starts from 1. You can say this I is equals to 1 to n. So this is 1.
We can't see the screen.
You can't see the screen?
Yes.
Yes, we can't.
Is it by choice or it's not visible completely? No, you can as well choose not to see. Is it?
No, someone.
Someone? Yeah.
Someone shared the screen when you were presenting.
Oh, now you can see.
Not yet.
No.
Can see you.
No, you know, it's not that it was just by mistake. He did it intentionally. Is it?
No, we are not seeing the canvas screen. We are seeing you.
You are seeing me?
Yeah.
Yes.
Oh, yeah.
Yes.
Who was presenting? Or I leave him to present, maybe. He might be having some burning issue he wants to present. Maybe. Okay, I can see. In fact, I think I'll check the recording so that I see who was that was presenting. Maybe. As I said, the problem with online, you can just reach a point, and if things are not adding up, you just say we are not seeing, and that is it. When you say like that, that means we have to stop. You can now see it, yeah?
Yes.
Good. So that guy, please don't present unless you have something burning that you want to present. So, so we are saying that this Q1 is common to all of them. Then this is Q2. So you'll have summation of Q2, all the Q2, Q3, Q4. So we can say, I think we should say this is what, J. Maybe we can put that to be J, because we don't know the value of J, or we put it to be I because we're using I here. Then divided by R n squared. Don't know how far it is. So that means we're embracing, because we can easily count the number of charges. So we go for the discrete summation and sum up everything. That's why we are saying that if you have these three charges, Q1 here, Q2, and Q3, then you can have a force of F13. There's another force F12. There is another force F23. Any other? So the total amount of force, you should add all this. You sum up this. So F should be equals to the summation of all this. Now, we only do this when it is linear. If it's not linear, you have to put this along the X and the Y. You remember how we did that question. And then sum up the X separately from the Y. Is that okay? Hello? Are we together?
No, kindly repeat.
Kindly repeat. Repeat. Look at these three charges. They form a triangle, right? Now, if this is on a surface, let's say we put it on the ground, all these charges are on the ground, but they form a right-angle triangle. You have to choose whether this is your x or this is your y, then you resolve this. Because we say that the resultant should actually be taking care of the vertical and the horizontal component. But if they are along a straight line, let's say there is Q1 here, there is Q2 here, and then maybe Q3 is somewhere here. Q3. So therefore, because they are linear, we just sum it directly down. Right? Now, this explains to why, if I take you back to this, we computed, you remember we said this is x and this is y. Then we computed along the x and along the y. Then finally we got the resultant. Are we together? But if this was along a straight line, you just sum directly. E should be equals to E1 plus E2 plus E3 plus E4. Right? Hey, can you respond?
Yes.
Yes. Yes.
Good. Yeah. So please take care. If it is along the linear dimension, you just add directly. If it is at an angle, you have to resolve the x component, the y component, and then find the resultant. I think that is clear. For engineers, those are basic stuff. So I don't think you have a problem. Now, spherical charge distribution. Charge normally resides on the surface of a sphere, not within the sphere. So it will distribute itself along this, because you read this to get more information. So this is where you find charge along the sphere. Now that means that if you consider the electric potential, which is the work done per unit charge, the electric potential will be a constant here. V will be a constant within the sphere, but on the sphere, it will be at a maximum value. Then when you move away from the sphere, it will be decreasing exponentially. I will explain that. Now, in terms of the electric field strength, we know E is given by V over D. So if E is given by V over D, now V is a constant, V is not changing, right? So we can say E is equals to dV over dt, of dV over d what? dr. dV is not changing, so therefore the electric field strength inside this sphere will be 0. But on the surface, it's going to be maximum, right? Then as you move away from the surface, it will decrease exponentially. So we'll be talking of, if you're talking of an area, then we'll be talking of surface charge distribution, which is given by sigma is charge per unit area. So this is surface charge distribution. You can have linear charge distribution. You can have volume charge distribution. So that will come later on, all right? So we'll explain how it comes to that. Now, of course, this will be Q over the volume, sorry, the area of a sphere is 4 pi r squared. Get that. That is the charge, surface charge distribution. So I've said, remember, charge distributes itself on the surface. Inside, there's no charge. So inside, V, the potential, the electric potential is a constant, but E is 0. Here, everything is at maximum, then it decreases exponentially. I think I need to demonstrate that on my canvas so that members can understand this. So what you're saying is, remember we said V is what? From our notes? V was what was E? And what was F? So from our notes, we said V is 1 over 4 pi epsilon naught. Take you back there. Our V is 1 over 4 pi epsilon naught, Q1 over R. Q1 over R. And then our E is V over D. Our E is V over D. So this is V over D, or you can have dV over, there's nothing that prevents you from writing dV over dt. dP, right? Maybe P is the distance, all right? Who is that? Somebody should mute his or her mic. Good. So then V, we said it's 1 over 4 pi epsilon naught. Sorry. One over 4 pi epsilon naught Q1 over R. So this is R and then Q1 like that. Now, when you're talking about sphere, you say that charge resides on the surface of the sphere. So inside this sphere, there is no charge distribution, correct? So all around, you have the positive charge on the surface. Now, there is no charge inside. So we are saying that, remember again, we say this E is what? F over Q naught, S to charge. So therefore, inside, there is no charge. So this E will be 0. Now, inside the sphere, the electric potential is a constant. That's why there is no change in dV. So therefore, V will remain constant inside. This is a constant. Then from the surface, as you move away from the surface, it will decrease exponentially. So what you are saying that for V, if you make a plot, then you will have something like this. Inside, let's say this is of radius R. Up to R, it's a constant. This is V against R. Then as you go away from the surface, it will decrease exponentially. You end up with that. Now, when you talk of E against R, you say this is E along the y-axis, then R along the x-axis. We are saying that inside here, there is no electric field strength because of absence of the charge Q. So this will be 0 up to R. Let's say this is your R. So this will be 0. And then at R, it goes to a maximum. Then beyond R, it decreases exponentially like that. So please take note of this and that. Are we together? Are we together? Hello? Hello?
We are together.
We are together. But anyway, must we be together? Anyway, no. It will be. Is it a must? No, it's not. It's not. So you can see E decays exponentially here. V will also decay exponentially. But within the sphere, E is 0. Within the sphere, V is a constant. Right? So that will give in this. This is your sphere of radius R. We are saying that the first part, this is E against R. E is 0. Then it goes to a maximum and then decreases exponentially. Then V is a constant up to R, but then it decreases exponentially. I think that marks the end of this section. So we said we need to demonstrate something here. Remember, from the surface charge density, we said sigma is equals to Q over per unit area, but the area is 4 pi R squared. So we can make Q the subject of the formula. You end up with this, all right? Then you can substitute for Q here. If you substitute Q here, everything cancels out. You remain with sigma over epsilon naught. So this will be the electric field strength on a spherical surface. Then similarly, the electric potential, substitute this Q here. You end up with sigma over epsilon naught R. This is important. Then we said inside, the electric field strength is 0. On the surface, it's maximum. Away from the surface, decreases exponentially. Electric potential inside the sphere is a constant. On the surface, still a constant, but at maximum. Away from the surface, decreases exponentially. Then this is the diagram. Reactions towards that, reactions. Can we react? Hey, can we react?
Excuse.
Yes, yes.
Do we have got this textbook we are using?
Yeah, I've given, of course, I gave the course outline. I'm going to circulate. I'm going to circulate it so that we see the reference materials that you need to look at. Then, two, I'm going to send my presentation. Of course, this lecture is being recorded, so I'll also forward you the recording for the lecture, all right? So that at your own free time, you have only 2 hours per week. Or can we create the 3rd hour? Is it possible? So that I can slow down, because the moment I slow down, we'll never complete this thing. It's so wide. Yes? Or ideally, since this lecture is being recorded, you'll look for your own free time to go through the recording so that you understand better. And then to keep you on toes, I think this section I need to bring an assignment over the weekend. Give it like some 2 days so that you can log in at any time and do it, so that you see whether you are getting some of these things. Right? I'll send the list of references that are being used, so you can go to the library and check. Then I'm also going to send you my notes, so your reference. Is that okay? Daniel?
Yes.
Thank you.
Murugi? Muiruri, do you have something you want to say? Muiruri?
No, sir.
Oh, you okay with everything?
Yes.
You okay with everything?
Yes, it's okay.
Good. So can I move to capacitors?
Yeah.
Capacitors? Can I move to capacitors? We have like 20 minutes. I think 10 minutes I would have covered something, right?
Excuse
now, we
me.
all know. Hello?
Before you move on.
Yes.
In calculating the intensity, the electric intensity at the center of the square, in that question you attempted, what did you do after you added and subtracted this, the charge that strengthens and weakens the field, like after that?
Okay.
Yeah,
now,
like what's the next step?
Okay, good. Now what we did, is that we said we had a square. Please assume this is a square. No, it doesn't look like one. We say this is along our y, and this was along our x, right? Yeah. Because this is not linear. So this angle is 90 degrees. This is x. Now, when you get, we had E1 here, I think, then E3 here, then E2 was here, and E1 was here. You remember that? Yeah?
Yes.
Then we said that these two were of opposite charge, so they weakened the field. That's why we subtracted them. E1 and E3 subtracted. Now these were of opposite charge, so they enhanced the field, the electric field strength. So we added this. Now you can see this gave you the y-axis, this gave you the x-axis. So if you have something like this, you need to find the resultant. The resultant will always be this, all right?
Yeah.
Then you complete this into a right angled triangle. So this component, EY, comes here. EY will come here. I think you did this thing in the mechanics, right? This is EY. Then this is EX, right? Then if I want to get this, I simply invoke the Pythagoras theorem from class 2. So this is EX, sorry, this is EX squared plus EY squared. Then I square root this. I will have obtained this value of E. Now, if I bring a test charge somewhere here at the center, here, then let's say this is Q naught somewhere there, then I can get the force experienced by Q naught due to E. So that will be F is equals to Q naught E. And that solves the other part that we have done. Is that okay?
Yes, thank you.
Yeah, but remember again, I said that electric field intensity is what? Is a vector quantity. So being a vector quantity, you need to define theta. So theta should be actually tan inverse of EY over
EX.
EY over EX. EX. Right. So you give this and that, and then compute the force like that. I think I'm tired. Right?
Me too.
Yeah?
We're also tired.
Oh, you choose to be tired now. Yeah? I'm tired. The students are also tired. It's a good point to stop, right?
Yes.
Now, let's discuss some issues here. We are engineering students, not just engineering, electrical engineering. The cutoff point for electrical engineering is too high. It's around 47 offered. Oh, there is electronics, guys. What? There is also mechatronics, or you don't do mechatronics. There is no mechatronics. So this is a class where we expect, like, I saw we actually 102. I expect to get like 50 S or on the lower side, otherwise 60 or 70 S. These are basics, right? So can we say maybe every weekend we have a test, just to keep you on toes? I mean, or that will be too much. I'll be demanding too much from you. Because I want, once I finish, something is once and for all. I don't go back there. Is that okay?
It is okay.
Or maybe you'll discuss and give me feedback.
Yes, we will discuss and give you back.
Then you have a WhatsApp group? Do you have a WhatsApp group that is functional? Somebody says kindly repeat. I think I repeated the SOMAS code. Of course, I'll create the unit, then give you the code. Oh, somebody saying paint. I think I need to go back to the drawing board and see whether I can get paint. Paint is an app, I think. Oh, somebody responded that an isolated system is a system that doesn't interact with its surrounding. That was good, because we say that there is no external force acting on the system. Oh, somebody had a problem with his or her mic, I think. Oh, Armstrong, the one we wanted to throw out. That's okay, it responded. So much, I will share that. So is there a WhatsApp group? Yep.
Yes. With Professor Coulomb.
With? I think I need to join, right? I need to be added. Is it? For specifically this unit, not is for everything. Hello? Marigu?
Muita, class rep, confirm.
No, you will, I think you will take care of that. You will take care of that. Ensure that the lecture is added to the WhatsApp group so that I can also see what is happening. Is it, you know, now it's like I'm living in a bush. I don't know. So ensure, Marigu, ensure that the lecture is added. All right. So any other question? Any issue that you need us to discuss? Any problem? Those who came late, I think I'm going to circulate the recordings. You can go through them. Then the lecture notes for this section are going to be distributed through the class rep. So class rep, please let me have your email address, both the two. Then I can circulate the lecture notes that I've used for this. Then also I'll give the one for capacitors, so that we go through them before next week, so that I can move to current electricity. Because I think that is what we are all waiting for. We are electrical and electronic guys, so we don't like this thing to do with the stationary charge. We need the charge to be moving, right? We can't understand why it's not moving. We'll get that next week.
Excuse, give us information on lab work.
Oh, lab.
Yes.
Now, I will conduct the chief technologist to confirm whether you're having your labs today, right? I think I saw it like there is a session today and tomorrow. Is it?
Yes.
Hello? Hello? Riani? Daniel, is that okay?
Yes, yes.
You have today and tomorrow.
Yes, in the timetable that is.
Yeah, so let me confirm with the technologists whether everything is set so that you can come. But if it's not set, then they will tell us when we are supposed to begin. Now, from your first semester, you know how to handle the labs, right? You know how to write your report? Because I can see many students are scoring very low marks. So I think that part I need to get time and repeat. All right?
Yes.
Yeah, because the scores are not good for the lab component. For physics 1A, the scores are not good. So we'll look into that and see if we can provide more information. Awesome. But that one, should it be at a fee? Because I'm supposed to be only teaching FEE 102, Physics B, not into the labs. But I'll give it. There's no problem. Because at the end of the day, we are combining the lab component and the theory. Sawa?
Yes.
Okay. So I think we can call it a day. We can go for lunch. If at all you are having lunch, nowadays you don't cook in the hostels. Of course, you'll be expelled from the university. Just go spend. I think help. They send the money. Your money is on the account. Good. Okay. Bye.
Bye.
See you.